In intensive care, a clean, accurate, invasive arterial blood pressure trace is a physiological lifeline, but that lifeline can lie. If the trace violently spikes, the monitor will display an artificially high systolic pressure. We assume the screen acts as a direct window into the patient's artery. It doesn't. The waveform is a heavily manipulated electrical output, and it is remarkably easy to distort. The error can swing the other direction too. A rounded, flattened curve on the monitor will dangerously underestimate the true systolic pressure. If you titrate vasoactive medications based on these physical artifacts, you are treating the equipment, not the patient. To generate an accurate reading, the biological pulse has to survive two distinct physical hurdles: fluid dynamics and electrical transduction. The kinetic energy of the pulse travels out of the radial artery, up the cannula, through a column of saline, into a plastic transducer, and finally out to the digital monitor. To trust the digital display, we have to reverse engineer the physical forces that create and corrupt it. We start at the electrical engine at its core. Inside the plastic transducer casing is a microscopic polymer diaphragm. Its primary job is to flex when hit by a pressurized fluid pulse. Attached to the back of that diaphragm is a strain gauge. As the pulse stretches the gauge, the wire becomes thinner and longer, forcing its electrical resistance to increase. The physics of measuring that tiny change in resistance was formalized in the 19th century by Sir Charles Wheatstone. This schematic shows a Wheatstone Bridge. It's an electrical circuit designed to measure microscopic changes in resistance that a standard voltmeter would completely miss. The circuit relies on four components: two fixed resistors, R1 and R2, one variable resistor, RV, and the unknown resistance of the strain gauge, Rx. When balanced, we achieve the null deflection principle. Electrical current flows equally down both parallel paths, bypassing the central bridge entirely. Early electrical engineers proved this concept with robust physical instruments. They tracked the exact balance of the bridge using a sensitive galvanometer. In a modern transducer, the patient's pulse stretches Rx, increasing its resistance. The bridge unbalances, forcing a tiny electrical current to cross that center bridge. That specific current is directly proportional to the patient's blood pressure. The Wheatstone Bridge is a near-flawless electrical translator. When a clinical waveform distorts, the failure is almost never electrical. It lies upstream in the fluid mechanics. We step backward, out of the transducer, and into the column of saline tubing connecting the sensor to the patient. Every physical system possesses a natural frequency, the inherent preferred rate at which it will oscillate when disturbed. The fundamental frequency of the human arterial pulse is low, between 1 and 3 Hz, but it is built from multiple higher-frequency harmonic waves stacked together. If a system's natural frequency overlaps with the pulse's harmonics, the waves erupt into a massively amplified signal. An isolated transducer's frequency is 45,000 Hz, immune to biological resonance. But adding a saline column drops the system's frequency to 15 Hz, dangerously close to biological harmonics. That 15 Hz drop is the exact physical cause of the jagged, underdamped systolic overshoot. The fluid column itself is resonating, artificially amplifying the pulse. Because clinical medicine requires a physical fluid column, the system's natural frequency is inherently compromised. To save the signal, engineers have to introduce physical friction. We call this friction damping. It is the intentional introduction of physical resistance to dissipate the kinetic energy of a system and suppress wild oscillations. Clinicians measure this resistance using a fast flush or square wave test. They blast the system with 300 millimeters of mercury of pressurized saline, forcing the tubing to reveal its damping characteristics. This Cartesian graph maps pressure over time. The sharp right-angle drop traces the release of the 300 millimeter flush. A system with a damping coefficient greater than 1.0 is overdamped. It's sluggish, taking too long to return to baseline, underestimating systolic pressure. In practice, overdamping occurs when the pulse's kinetic energy is absorbed by overly compliant tubing, microscopic air bubbles, or blood clots. At a coefficient of exactly 1.0, the system is critically damped. The trace returns smoothly to baseline and prevents all oscillations, but it is too slow. Optimal damping, set at 0.64, preserves a rapid response time by accepting a predictable 7% overshoot. For the clinician at the bedside, the visual cue is strict. A perfectly tuned system will always produce exactly 1.5 to 2 oscillations following a fast flush test. The damping coefficient proves that accurate monitoring isn't about achieving perfect signal transmission. It requires engineering a mathematically precise amount of signal degradation. The Wheatstone Bridge provides flawless electrical sensitivity, but it remains entirely at the mercy of the fluid column delivering the mechanical kinetic energy. The tubing architecture must follow a strict physical checklist. It has to be as short, wide, and stiff as clinically possible. Short and stiff tubing minimizes fluid mass and compliance. This pushes the system's natural frequency as high as possible, safely away from biological resonance. Any compressible air bubbles or excessive stopcocks introduce catastrophic friction, driving the damping coefficient past 1.0 and ensuring an overdamped failure. Mastering the invasive arterial line requires stepping out of the purely medical mindset and acting as an applied physicist. Every digital waveform you see is an ongoing negotiation between electrical resistance and fluid friction.